Hello, and welcome back to Short Text 331. Today, we're going to continue our series on linear systems of equations, and this is part 3. Now, to get started here, let's consider this small system of equations, pretty much the smallest non-trivial you can have, this 2 by 2 system, and your coefficients then will be a, b, c, and d, and your unknowns are x1, x2, and your right-hand side is given by y1 and y2. And you can write it in matrix form, matrix vector form in this way, with your matrix being a, b, c, d, your unknowns being x1 and x2 in a vector form like this, and your right-hand side being y1 and y2. Now, how do we solve this type of system in practice? We don't really use matrices to solve this type of problem. We really just do it by hand typically. But just to fix ideas, let's go ahead and go through the solution of this problem, and so we can get an idea of how we're going to tackle this in the general case, and also get some insights into what might work for much larger systems and what might fail. Now, if you take your second equation here, you can solve easily for x2. You go ahead and you put cx1 on the other side of the equation, and then you divide by d, and you obtain x2 equals to y2 minus cx1 divided by d. And we're assuming that d is non-zero, so that it makes sense to solve for x2. If d were 0, then x2 wouldn't even be on that equation, and so we don't have a problem with that. x2 then is equal to y2 minus cx1 divided by d. And we go with this expression and we insert it in here next to b in the first equation, and that's what I do down here. I grab the first equation and replace that, and so we get this combination. And what we're going to do next is simplify it by multiplying by d across the whole equation. And if you do that, you get dax1 plus by2 minus bcx1 equal to dy1. And from here, what we're going to do next is group all the terms that depend on x1. That's what I've done down here. dA minus bc multiplied by x1. That's the first term and the third term. And then the second term, I'm going to put it on the other side of the equation. And so I get dy1 minus by2. So what happens next? Well, we're almost there. We go ahead and we take x1, we divide by dA minus bc, or we put this on the other side of the equation if you want to think about it that way. And we obtain what's in this rectangle here. x1 is equal to dy1 minus by2 divided by dA bc. And from here, you can go ahead and insert x1 up here to solve for x2, or you can do it in a different way by going through this whole song and dance again and solving for x2. And what you obtain is this, what's in this rectangle here. You obtain that x2 is a y2 minus dy1 divided by dA minus bc. And this is a completely general solution of the 2 by 2 problem. You can write this down and you have it once and for all. Now you note right away a couple of properties of this solution. So first of all, the solution is nonlinear in the matrix coefficients a, b, c, and d. So the equation is linear. It's a linear equation for x1 and x2. But as far as the coefficients of the matrix are concerned, they will appear in a nonlinear way. As you can see here, they appear dividing. The second thing that you notice right away is that we will run into trouble if our matrix has this property, that dA minus bc is equal to 0. If this is true, you can take the first equation, ax1 minus bx2 equals y1, you multiply by d across like I did here, and then you get to change this dA to bc, because that's what this equation is telling you. If dA is equal to bc, so this combination is 0, then this dA can be flipped to bc. And if then this equation would be true, bcx1 plus dbx2 is equal to dy1. But then I can divide by b on both sides of the equation, and I get cx1 plus dx2 equal to dy1 divided by b. Why is that a problem? That could be a problem. That could be a problem because this is a lot like the second equation we got. Our second equation was cx1 plus dx2 equals to y2. Let's go up here. Our second equation was cx1 plus dx2 equals to y2. Let's go back here. And now this equation, if this property is true, that equation would become cx1 plus dx2 equals to dy1 divided by b. So this is coming from the first equation. And this would be trouble. This could be trouble because if dy1 divided by b is not equal to y2, then there will be no solution. Then we'll have two equations that are incompatible. Remember, I derived this using the first equation and this property, nothing else. And the second equation tells me that actually this combination has to be equal to y2. So if those two things are not equal, then I have no solution. The system is incompatible and I cannot solve it. Of course, if y1 is equal to y2 is equal to 0, then there's always a solution, and that remains true. If y1 is equal to y2 equal to 0, then those right-hand sides are both 0, and there's no problem. But if they're not equal and dA minus bc is 0, then you'll be in trouble. Now, if they are equal, if y2 is equal to dy1 over b, then again, under this condition, what you have is two equations that have the same information. You have one equation that tells you cx1 plus dx2 equals this, and you have another equation that tells you the same thing. And so that tells you that you would have two equations with no new information, so really just one equation with two unknowns. One equation with two unknowns, and that means you have an infinite number of solutions. If you enjoyed this video and the series of videos in general, please like and subscribe. If you're looking for a tutor in physics or math and you're not a student at UNC, then maybe I can help you. You can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. Now, this peculiar property, this peculiar quantity, dA minus BC, is called a determinant. And in this case, it's a determinant of a 2x2 matrix, and it can be generalized to any matrix. We'll do that later. But in this case, we usually, actually in general, we use the notation det A to denote the determinant of A. Sometimes we use these parallel bars around the matrix, or maybe explicitly around the matrix like this, to say that we're interested in this determinant, to denote the determinant of this matrix A, B, C, D. And the determinant is then calculated in this way, AD minus BC. So you can think about it this way. Cross, and you subtract the two. And that's what you get for the 2x2 case. For the larger cases, 3x3 or 2x3 or other cases, there's going to be another definition that will that is of course compatible with this one, that we'll talk about it in a future video. Now, when this determinant is 0, we run into trouble as mentioned above, and that remains the property for larger systems as well. When the determinants are 0 is something, or very close to 0 in numerical situations, these are places where you want to be careful because you may run into trouble. Now, with that out of the way, how do we solve the general square problem? We're going to stay with the square problem, ax equals b, assuming that we know that there's no trouble. Assuming that we know the determinant is non-zero, so there's no problem. So how do we proceed? One way to proceed was developed a long time ago by Gauss, and it's called Gaussian elimination. Let me show you this first with an example. So let's consider once again a 2x2 case. This matrix 3, 4, 5, 2 multiplied by x1, x2 has to be equal to 7, 7. This is what we want to know. And in fact, if you look at this equation for a little bit, you see that, well, maybe the solution is not hard, because 3 plus 4 is 7, and 5 plus 2 is 7 also, and so the solution is 1, 1. So we really already know the solution. This is a very simple example. But let's go through the motions of this Gaussian elimination algorithm to see how it works. So the first thing that you do when you're given this problem is you form this enlarged matrix. You take this matrix, you put it in here, and you take the right-hand side and you attach it to the right side of your matrix. So you get 3, 4, 7, and 5, 2, 7 as your elements of interest. We're going to take the first row and we're going to divide it by 3. And so imagine you take that first row and you make a copy of it on the side and you divide it by 3. So you get 1, 4/3, and 7/3. That's by dividing this first row by 3. And now what we're going to do next, we're going to multiply that by 5 and subtract it from the second row. So we multiply this whole thing by 5. So we get 5, 20 divided by 3, and 35 divided by 3. And we're going to subtract it from the second row. And we multiply by 5 because there's a 5 here, and we want to turn that into a 0. And so we take that and we subtract that from the second row, so we get 0. Then we get our 2 minus 20 divided by 3, and our 7 minus 35 divided by 3, because we're subtracting these objects from the second row here. And if you do the calculation, you see that you get our first row, which you could divide it by 3 if you wanted to, or you can just leave it untouched. Either way is fine, it'll give you the same answer. And you get 3, 4, 7, and 0 minus 14 divided by 3, and then minus 14 divided by 3 again. And what we've accomplished with this is that we've performed some elementary operations which are allowed, which is taking an equation here, taking, if you want, our first equation and multiply it all by some number or divide it by some number, and then subtracting that from the other equation, which is also something we're allowed to do. We're allowed to add and subtract one equation from another equation. That's a perfectly allowed operation, but we've used that symbolically here to try to get our problem into a triangular form. So we have an upper triangular form. Once we've arrived at that point, then we can solve the last equation here. We rewrite now the equations in the new form. We have 14 divided by 3 with a minus sign times x2. It has to be minus 14 divided by 3 again, so x2 has to be 1. Very easy to see. And then if you go ahead and you put an x2 equal to 1 here, then you see right away that x1 also has to be 1, because 3x1 plus 4 equals 7. You put the 4 on the other side of the equation, you get 3x1 equals to 3, and so you see that x1 is equal to 1. And this is how you solve it. So in other words, the Gaussian elimination is all about performing elementary operations multiplying by constants and subtracting one row from another row and so on, so that little by little you can convert your whole system into a triangular form. And once you have it into a triangular form, you go back to your original notation in terms of equations, and you start with a bottom equation, and you solve it, and you replace that in here to solve for x1 and so on and so forth, all the way up to your first equation. So let's look at then at the general case to see how things work out. So this is our general case. Suppose we have this our n by n system of equations. We're given all these constants a11, a12, and so on, all the way to a1n. This is our first equation, equals to b1, and then we have a similar second equation all the way to ann xn equals to bn. So these are our system of n by n equations, so n equations with n unknowns. And if we put that in matrix form, the form required by the algorithm, then it would look like this. We have an n by n matrix of numbers, and then we have n components here on the side denoting the right hand side, and that's our starting point. So the first thing we do is we take that first row and we divide it by a11. Take that first row, divide it by a11. And then once you have that, you set it aside and you multiply by a21, you subtract from the second row. And if because you multiply by a21 and you subtract from the second row, you're going to obliterate this element. So once you do that, that element is going to be 0. And then you go back to that copy of your first row that you divided by a11, and now you multiply by a31, and you subtract that from the third row. And in that way, you accomplish that you get a 0 here as well. Whatever happens to the other elements doesn't matter. The point is that we're trying to turn this into a 0, and the next one into a 0, and the next one into a 0, and so on and so forth until we get to the last one. So that's why we have n steps here. We're going to do that n times, or if you want, n minus 1 times actually, so that we get zeros all over here. And that is perfectly allowed. So we took one equation, we divided by one constant, we multiplied by another constant, one at a time, so that we can subtract from each equation what we need to subtract to eliminate all these zeros. That's why it's called Gaussian elimination. We eliminate all these elements. Now, we are now a step closer to getting this into triangular form. Now we have to deal with this smaller case. And so we leave the first row as it is. We don't worry about it. And then we take this second the second row here, we take this sub problem and we divide by a prime 22. So now I call this prime because it's not going to be the same one as this a22. So this a22 prime is going to be whatever happened after you subtracted this a21, multiplying the previous row and dividing by a11 and multiplying by a21 and subtracting that from second row. So something up here or there, in the same way that in our example we had some modified elements here. So something was modified there, and we obtained these primed elements. But the main point is that after this first step, with the sub steps, you're not with the same first equation, and then you have a smaller system here. And what happens next? You go and you do the same thing. You divide by a22 prime, you multiply by a32 prime, and in this way, by subtracting from there, you eliminate all the elements under that a22 prime. And you get 0, 0, 0, 0, 0 all the way to the bottom. And you continue with this process. You repeat this process, and now you apply to the smaller matrix. And at some point, the process will finish. And when the process is finished, you will obtain then an upper triangular system of equations because you've obliterated all these elements, so you've turned them all to be 0, except this one here, which when you get to that point, you just let it be, and you don't have to worry about it because that is the first equation you're going to solve once you're done with this process. Once you've achieved this point, then that last equation is trivial. You solve for xn by taking this element, dividing by this element. And once you have xn, you go to the previous equation, you solve for xn minus 1. And once you have xn minus 1 and xn, you go to the previous equation, you solve for xn minus 2, and so on and so forth. And that's called back substitution. You go all the way to the top, and you end up solving for x1 at the very end. And this is something we saw before. In a previous video, we discussed how to solve systems that are upper triangular. You can play the same game and try to make this lower triangular instead. The classical case here is to make sure that your system is upper triangular instead of lower triangular. So all the non-zeros are in the upper triangle of the matrix. And we saw exactly how to do that. But what this provides you, what this Gaussian elimination provides you, is the algorithm, the steps that you have to follow in order to turn your general system into an upper triangular system. And the claim is that if the determinant is of your matrix, which we've seen only for 2 by 2, and there's a more general definition for the more general case, but if that determinant, as I say up here, is non-zero, and you know that the solution exists and there are no issues, then this algorithm will give you the answer. Okay. It may be that you have to switch some columns, that you have to switch some rows, that you have to reorder your equations a little bit. But other than that, this algorithm will give you the answer, and it's what we call one of the direct methods to solve the problem, because you pursue a finite number of steps. Your matrix is written entirely from the beginning. You pursue a finite number of steps, you turn it into an upper triangular form, and then you go and you apply what we saw before, that is the back substitution algorithm to solve upper triangular systems of equations. That's it. That's all I have for you for this video. I hope you enjoyed it. If you did, please like and subscribe. And as always, I'm happy to help you if you're looking for a tutor in physics or math, in English or in Spanish, as long as you're not a student at UNC. And just shoot me a message at shorttakes331@gmail.com or leave a comment in the comment section below. Until next time.